Hello everyone, welcome to our presentation today. We'll be talking about the modeling intertidal elevation using tidal data within the Africa platforms. I'm Joseph Tishimire, so I'll be playing this on behalf of Paul Sidiki, who contribute to the preparation of this PTT. As you all know, the Africa is a program that was initiated by the government of Australia via Geoscience Australia, and the idea was to uh, provide flexes uh, to satellite data to all users with the continent, and so that all decision makers, academicians, the private sector, even NGOs, should have um, enough evidence to inform environmental, socio-economic changes on the continent. And we align with several programs like AfriGeo and the others across the globe to identify some gaps in EU datasets and to provide related capacity building for the continent. And we provide open and free data. Our services operate at continental level and be sure that everything you do is accountable and transparent enough, and we leave no one behind, being broken as a continent, and also uh, being any language, age, and also gender. We are a program that operates at continental level in Africa, and our datasets are hosted in Cape, South Africa, at AWS server, and we thank space agencies, especially USGS and ESA, who provide raw data and process them to make them available to the public in analysis-ready format. Our services are completely free, even for commercial use. They can be accessed either online, reduced online computation, or can download them and use your PC. And also, we have a free online learning platform and help desk just to make sure that everyone has enough capacities to capitalize data services. Everything we do is run with SDGs, and we try to provide uh, data at the continental level and generate services depending upon the user's needs. So far, we have 5 bytes of data sets, and also we think some institutions, especially regional centers, uh, including Oasis in Tunisia, um, and CSC in Senegal, Agreement in Niger, Afrois in Nigeria, RSMRD in Kenya, and many other national space agencies across the continent who have contributed to the development and validation and dissemination of our products and services. So far, the services you see uh, on the right hand were developed by the Africa in collaboration with partners with the continent. So we have the geomats, these are called free mosaics, derived from Landsat limited resolution and the Sentinel limited resolution. Imagine the work of all image processing was done by the team, and you access datasets in the analysis-ready format. The cropland extent map that was developed in collaboration with partners to map cropland areas with the continent, the fractional cover, and then the chromatologies that inform the trend in greenness, mostly monitoring crop health and phenology, and what was using from space to inform long-term water management, and also the coastline service to monitor the trends on the coastlines across the continent. Today we'll be talking about um, the tidal modeling and using the sandbox, which is a cloud-based computational platform that operates through a Jupyter Lab environment. It provides a limited but free computing resources for technical users and data scientists to explore the Africa dataset and the product. And you see the notebook we'll be using is under the folder, um, under the notebooks, and the layout examples. And this notebook will help people to um, um, kind of and this is really available on the cloud, and you can access it and also go directly to the modeling. So what do you call intertidal zone? The intertidal zone is the area where the ocean meets the land between high and low tides. It is covered by water at high tide, and of course, it is exposed to the air when you have low tides. The area can include many different types of habitats, including steep rocky cliff and beaches or wetlands. We have four physical divisions, each with distinct characteristics and ecological differences. And those are spray zones. Those are dampened by ocean spray or high waves, and they submerged already with very high tides or severe storms. We have also the high zone with those one floods and during the peak of daily high tides, but remains dry for long stretches between the high tides. It is inhabited by hardy sea life that can withstand pounding waves, such as barnacles, marine snails, mussels, limpets, shore crabs, and hermit crabs. At the middle, the tidal zones over which the tides, where the tides ebb and flow twice a day, and which is inhabited by a greater variety of both plants and animals. This includes sea stars and others. With the low zone, this is visually the virtual is underwater during the lowest of spring tide. Life is more abundant there because of the protection provided by the water. As you see on this graph, the zones were delineated from the low, mid, high, even the spray zones described before. And the sea is increasing. It is colonizing a kind of, as tides are increasing, they're kind of colonizing from the low to the spray zone. So if we go to the case for the Africa, you know, the zones are faced with increasing threats from coastal erosion, land reclamation. For example, when you're developing infrastructure like ports, construction, and of course the sea level rise. And also the accurate elevation data describing the height and shape of the coastline is very needed to help predicting whether and where these threats will have the greatest impact. But the data may be always expensive and challenging to map entire the whole continent, like Africa. The rise and fall of the tide can be used to reveal the three-dimensional shape of coastlines by mapping boundaries between water and land across the range of known tides. mean that from the low to the highest tide. And also assuming that the land water boundary is a line of coastal height relative to mean sea level. Elevations can be moderate for the area of coastline, so located between the lowest and the highest observation tide. Imagery from satellites such as the ones from NASA's GS, Landsat, are available for free, and they can us to make a 3D model um, of the zones from regional to national scale. The same, even Sentinel-2 and other sources of e-water sets could be part to model the intertidal zones. So we can demonstrate how simplified version of national digital elevation model method combine data from Landsat from 5 to 8 or Sentinel-2 with the tidal modeling, image compositing, and spatial interpolation techniques. We first map the boundary between land and water from low to high tide, and secondly, we use this formation to generate smooth, continuous 3D elevation model of the intertidal zone. The resulting data may assist in mapping the habitats of certain coastal species, identifying the coastal areas of coastal erosion from hotspots to others, planning for extreme events such as storm surges or flooding, and improving models of how sea level rise will affect the coastline. And Bishop Taylor and the team have developed the methodology, and this has been previously used in Australia that to monitor the coast of the country. And if you see the model, first of all, from raw satellite images like Landsat or Sentinel, we can compute the normalized difference water index just to separate land and aquatic areas. And also we can derive the tide height, as you see. And from the tide height, you have some multi-layers, um, extremely high or extremely low. And also we can create a time series depending upon each tidal range. Now we have from the first interval, usually here are defined intervals. And also we can interpolate depth contours and in a continuous utilization model. And we can also extract if there is the topography of the tidal zone, the depth contours, and then you can therefore finally have a continuous DM for our region. And if we go to the applications, we look to enter the sandbox. We have a notebook, another examples called in modeling tidal elevation using tidal data. This will be using Landsat from 5 to 8. And each notebook starts by introduction, as I've been talking about the reason behind the change, the dynamics of intertidal elevation, and then there are the case. These have been applied by the Africa for the coastlines mapping, and also even for the mapping of the mangrove vegetation across the continent. And this will be consist of several steps: loading raw data, computing water index, sort images by tidal height, and create a time series or somebody call it a summary image composite, and they also start to use the contours and also create a continuous derivation model. Of course, we'll be loading the packages and the functions that will be used, and then we could be creating a local task cluster just to chop our level study in several tiles that kind of easy to make the task to our memory, and also we'll be using the application called intertidal elevation. And of course, we always define the area of study, either using latitude, longitude, and buffer, or loading a polygon over study area. And of course, we'll be defining our time scale. And this was done, and also our time from 2014 to 2020. And this is our area of study, which is, if we try to see, which is some errant Omoros. And we can load the state images, and you see have 174 time steps for this data set, and then you can adjust the images to the area of study, and then you can visualize a true color of one time step. Was 2014, May 2022, and then you can create the water index. This is an example of water index for a displayed image up there. And also you can model the tidy height by the formula, the kind of the up that we developed here, and I mean the function, and then those are tides, and also you can make kind of uh, uh, kind of composite or index summary based on the tidy height. As you can see, that you have defined the tidy height intervals, that you define the 9 intervals or the tidy height, and you can display images in the NDWI for each tidy height interval or over time. And finally, we extract the contours. This would be something considered the shorelines in the area of the coastal erosion monitoring. And then we can also kind of do interpolation, converting the contours into a continuous DM. Of course, that shows how the integer elevation is behaving as a DM, and also we should also mask other areas just to remain with aquatic areas, because when we deal about to deal with the integer elevation, we are mostly dealing with aquatic areas, and that's why you should ignore other aquatic areas. This was done either using Landsat or Sentinel. That was using Landsat, but also can use Sentinel to data sets, and the approach is the same. And we can have this the real time, the true color images, image show for this 23rd July 2018. And then you can create the water index. They're showing the aquatic areas in the blue and other non-aquatic areas in the dark red. And then you can model the tide height, define the intervals, and then display the time series and the image for each interval. And then we can use the contours, and finally we can produce a continuous DM, and also after mask out non-aquatic areas, and have this in new elevation for all our layers, particularly depending upon the tide height. So the applications were so many, but the first one was while we were developing the the coastal erosion application. I'm sorry, it is still running, but if we go to the mapping of the mangrove vegetation, the same model has been applied just to smooth the, for example, here, we use this model just to kind of filter satellite images by uh, tide height, just to remove the noise, so that you could many the aquatic areas and aquatic areas, and even map the mangrove in a very precise way. So this this approach has several applications, and I would advise all of you to go through our website, get more information about this application, and also you can keep visiting our communications. Most importantly, this session every Wednesday at 11 GMT, and also our website is always accessible. And so we have several courses just to equip you with the required skills to use these applications, especially the course on the coastline uh, is using the same approach just to map the trend or the coastlines for the continent, and also assess some effects on both coastal infrastructure and ecosystems. And of course, we thank our partners across the continent, from the state government and the other funders, and also people who had been providing technical support, especially our IPs. And of course, like to reach out to us, please scan the QR code, or even write us an email. Myself, Ken, and also Edward, our technical manager, is available for the support. Thank you, everyone. And the floor is just for questions and comments. Thank you once again.